Welcome to Built, Wired, and Secured, the podcast where we explore how modern buildings are designed, connected, and protected in the real world. I'm Alex Morgan, and in today's episode, we're diving into power quality and transfer dynamics, why it matters, where projects usually go wrong, and what decision makers need to understand before problems show up in production. Joining me today is Michael Harrington, and together we'll break this down from a practical, real-world perspective. Cold open. Imagine it's 2 a.m. A storm knocks out the utility feed. The generator kicks in, and the automatic transfer switch flips the building over. But a cluster of access controllers and elevator controllers reboot in a way that leaves them in a fault state. Tenants can't badge in. Elevators go to restricted mode, and a handful of critical HVAC controllers stop responding. No one lost power entirely, but operational technology is down and tenant operations are stalled. That's the invisible risk we're talking about today.
From an operational standpoint, that scenario is all too common. Tenants feel it immediately. Lights might be on, but business processes stop. What breaks if this goes down? Access, life safety interfaces, point-of-sale systems, network edge gear. You can have power present and still be functionally offline.
Why does that happen? Why would equipment fail when a generator is doing its job? Today, we'll unpack the causes: harmonics, UPS sizing and runtime, ATS transfer timing, neutral distortion, then talk trade-offs, and finally, what facilities and IT teams can do to reduce surprise downtime. By the end, we'll give you a short checklist and some simple transfer tests you can run during handover.
Let's start with the causes. Harmonics show up when you have lots of nonlinear loads: LED lighting drivers, variable frequency drives, server power supplies. Those distort the waveform and can overload neutrals and UPS components, even when voltages look nominal. Then you have UPS sizing mismatches. A UPS that was sized for steady-state runtime, but not for inrush currents or harmonic heating, will trip under real load conditions.
Can you explain transfer timing? I hear phrases like soft transfer, hard transfer, make before break. What should teams watch for during design and commissioning?
Sure. A soft transfer attempts to synchronize the generator and utility before switching, reducing transient voltage and frequency jumps. Hard transfer breaks the utility first, then connects the generator. That can create voltage sags or phase angle jumps that sensitive controllers interpret as faults. Automatic transfer switch, ATS, settings and actual switch timing matter more than most teams realize. If the transfer window is too short or the ATS sequence isn't tuned for the loads it serves, you get nuisance trips.
Neutral currents and distortion are another piece. How do they show up in everyday systems?
Neutral distortion comes from unbalanced nonlinear loads. In practical terms, you might see breakers heat up, odd voltage between phases, or protective devices tripping intermittently. Equipment with sensitive power supplies might reset or corrupt firmware during the transients. It's not dramatic like a blackout. It's the slow, flaky failures that make troubleshooting take days.
That leads neatly into trade-offs. Michael, when teams choose between a centralized UPS plant and point-of-load UPS units, what are the practical considerations?
Central UPS plants give efficiency and easier centralized maintenance, but they create single points of failure and complex transfer dynamics when paired with generators. Point-of-load UPS units, small UPS at racks or critical devices, localize the risk and often handle inrush and harmonics better for sensitive electronics. The trade-off is higher capital and dispersed maintenance. From an operational standpoint, decide which systems must stay up at all costs and isolate those with dedicated, tested solutions.
And soft versus hard transfer again ties to cost and complexity, correct?
Exactly. Soft transfers and synchronous controls reduce transients, but add controls complexity and cost. Hard transfers are simpler and cheaper, but increase the risk of nuisance trips for sensitive gear. The smart approach is a mixed strategy: soft transfer for life safety and tenant-critical systems, point-of-load UPS for edge gear, and clear ownership of the transfer sequences in maintenance plans.
Let's shift to implications and operations. What should facilities and IT teams prioritize in day-to-day practice to prevent the late-night surprises we opened with?
Priorities are simple and pragmatic. 1. Monitor meaningful signals, not just power present, but waveform quality, harmonic content, and UPS input-output anomalies. 2. Rehearse transfers on a schedule. A transfer test isn't a checkbox. It's a rehearsal with all critical systems observed and post-transfer validations completed. 3. Require transfer sequence documentation at handover with responsibilities spelled out for vendors and facilities. 4. Maintain a prioritized list of point-of-failure systems and protect them with local UPS or isolation transformers.
What are simple tests teams can run during handover that don't need specialized lab equipment?
Start with a staged transfer test. Identify a low-risk window and switch the ATS while observers watch access control, elevators, critical HVAC, and IT edge devices. Capture logs from UPS and ATS controllers and confirm that controllers reboot cleanly and controllers report in to central management. Use inexpensive power quality loggers for 1 week to spot harmonics and sags during normal loads. Finally, do a cold transfer test at least annually to see how equipment behaves under non-synchronized events.
Let's wrap up with clear takeaways. Michael, what should listeners do in the next 30 to 90 days?
First 30 days, ask for ATS and UPS transfer logs from your contractor and review who owns transfer sequencing in your maintenance agreement. 30-60 days, schedule a staged transfer rehearsal with observers for all tenant critical systems and collect post-transfer logs. 60-90 days, deploy temporary power quality monitoring in known trouble areas and prioritize point-of-load protection for the top 3 tenant impacting systems. And throughout, document the findings and make them part of capital planning.
Those are practical steps. Monitor waveform quality, rehearse transfers, protect critical edge systems, and bake transfer ownership into contracts and handover. If you follow that sequence, your chances of an invisible but devastating failure drop significantly.
One closing note. Always involve licensed electrical professionals for changes. These are system-level decisions. Get the right people, run controlled tests, and treat transfer rehearsals as operational exercises, not once-and-done events.
That wraps up our discussion. We covered how harmonics, UPS and ATS interactions, and transfer timing can silently disrupt building operations, and we gave a short roadmap for testing and protection that property teams can actually execute. For a downloadable checklist and a transfer test template you can use during handover, visit our site and grab the resources tied to this episode. Built to last, wired with intention, secured for the real world. That wraps up today's episode of Built, Wired, and Secured. We covered practical steps to make power resilience measurable and repeatable, and hopefully gave you a clear way to think about how these decisions play out beyond the initial install. Thanks for spending time with us. Until next time, make sure the systems you're responsible for are built to last, wired with intention, and secured for the real world.